Welcome to the video lecture for Math Science 2060, Section 15.4, Polar Coordinates. In this section, we'll review polar coordinates, we'll look at how we can define a polar rectangle, and then we'll look at how we can perform double integration over domains that are defined in terms of polar coordinates. First, let's recall polar coordinates. Now, if we're in the xy plane, and we have a coordinate that's defined by the x and y position, shown with this black dot here, we can also represent that point using polar coordinates, where rather than using xy, we represent the point as a length, given by r, and an angle from the x-axis given by theta. In other words, this point can be represented in terms of r and theta, or in terms of the coordinates x and y. Now, the relationship between x and y and r and theta is given by these three equations. First, r squared will be equal to x squared plus y squared, and this follows from the Pythagorean identity that applies to right triangles. Secondly, the x-coordinate is going to be equal to the length times the cosine of the angle that's created with the x-axis. And the y-coordinate is going to be given by the length r multiplied by the sine of the angle theta. In calculus, we encounter many regions that are easier to define in terms of polar coordinates than in terms of Cartesian coordinates. When we define a function's domain in terms of polar coordinates, we call that region a polar rectangle. In this graph, we have a simple illustration of a polar rectangle, in which the r coordinate is bounded below by the value a and bounded above by the value b. Similarly, the angle is bounded below by the quantity alpha and above by the quantity beta. So when we're mapping out the polar rectangle, we're going to take the minimum value for the angle alpha, which comes from the x-axis, all the way up to the maximum value for the angle, which is beta, and that leaves this region in between the dotted lines. However, the region only starts when the length r is allowed to equal a, which is given by this lower segment of the region. And again, we see the maximum value of the region, or the region stops when r equals b, which is the maximum region, or the maximum value that's allowed for r. And the polar rectangle is going to be any set of points that live inside those boundaries. Using the same idea as we saw on the previous case, we can use polar rectangles to define more complicated geometries. Indeed, in this example, we can see that the variable r is going to be bounded below and above by a function of theta. All the same principles apply as before, but now we can see that the geometries of the top and bottom curves can become more flexible. Next, we introduce the equations for evaluating a double integral that's defined over a polar rectangle. In the first case, we'll consider a polar rectangle that's defined with the lower bound of r equal to a and an upper bound of r equal to b, and where the angle theta is bounded below by alpha and above by beta. Now, we do want this r value to be positive or non-negative, and we also want the difference between beta and alpha to live between 0 and 2 pi. In this case, we can start with the Cartesian integral, and we can move it to the polar coordinate integral by first taking the integral from alpha to beta, which is the angle variable, next from a to b, which is the distance or length variable, and then everywhere in the function that we have an x-coordinate, we're going to replace it with an r times cosine theta, and everywhere in the function that we have a y variable, we're going to replace that with r times sine theta. Now, another very important difference is when we move to polar coordinates, we have to introduce this r scaling. So when you write the dr d theta, make sure that you put an r in front of the dr term. If our function is defined over a polar region where the r value is given is a function of theta on its lower bound and a function of theta on its upper bound, the formula for the double integration is going to be very similar, in that we're first going to integrate from alpha to beta, and then we're going to integrate from h1 theta up to h2 theta rather than from the constants a and b. Again, in the function, every time we see an x-coordinate, we're going to replace it by r cosine theta, and every time we see a y-coordinate, we're going to replace it with r sine theta. And again, it's very important that we don't forget when we're taking dr d theta to add that r value. Next, we look at an example of how to evaluate an integral in polar coordinates. In this problem, we're asked to integrate the function 3x plus 4y squared over the region R, where R is the region in the upper half plane that's bounded by a circle with radius 1 and a circle with radius 2. Indeed, in Cartesian coordinates, we can describe this region as being the set of points in which y is greater than or equal to 0, because we're in the upper half plane, and x squared plus y squared is bounded below by 1 and above by 4. We can re-represent this region in polar coordinates by noticing that r can vary between 1 and 2, and I apologize, that 4 is a typo, and that the angle can go between 0 and pi, because that's the upper half of the plane. Now that we've established the region R in terms of polar coordinates, we're ready to set up the polar integral. So we're starting with the double integral over the region R of this function. And when we move to polar coordinates, we're going to start by taking the lower bound of our angle, which is 0, and we're going to integrate up to the upper bound of our angle, which is pi. We were also able to identify that the lower bound of our r value was 1, while the upper bound of our r value was 2. Everywhere in the function that we have an x value, or an x variable, we're going to replace it with r cosine theta. And everywhere in our function that we have a y value, we're going to replace it with r sine theta. Since y is squared, this becomes y squared sine squared. Again, when we include the dr term, we have to be sure to add an r variable. So we make sure that we have our r. And then our order of integration goes dr d theta. So the next step, we distribute the r throughout the function. And now that we've distributed the r, we can integrate this function with respect to r. Okay, it's a fairly straightforward integration. And our bounds of integration go from 2 to 1. Next, we evaluate this definite integral in terms of r, which gives us the constants 7 and 15. And at this point, we want to be sure that we don't have any r's left in our equation. If there was an r left here, we'd know that we've done something wrong. Our integral should only have theta variables at this point. So then we have to think about integrating this. And as you recall from Calculus 2, to integrate the sine squared function, we need to use the double angle formula. So we're just going to modify our equation. And of course, there should be a d theta term here as well. Okay, the next step, we're going to actually integrate this function. So we're going to get 7 sine theta, 15 over 2 theta, minus 15 over 4 sine 2 theta, from pi to 0, and that gives us the answer of 15 pi over 2. In this next example, we're asked to use double integration to find the area enclosed by one loop of the 4 leaved rows r equals cosine 2 theta. Now, as you may recall from Calculus 2, the shape of this curve is given as follows. And we know that one leaf of that 4 leafed rows occurs when we allow theta to vary between minus pi over 4 up until positive pi over 4. So we can represent the domain of this leaf using this polar rectangle, where theta is allowed to vary from minus pi over 4 to positive pi over 4, and r varies from 0 up until a function of theta cosine 2 theta. So finally, now that we've defined the region in terms of polar coordinates, we can think about evaluating its area. Indeed, if we want to find the area of the region D, or the area of one leaf of the curve, we're going to integrate over that region, but we're going to integrate the constant function. So we're really integrating the function 1, and often that 1 is just omitted. So you'll see an integration that looks like this when you're looking for the area of the region. So now we're going to transfer the integral over to polar coordinates. So for the bottom part of the angle, we're going to plug in minus pi over 4. For the top part of the angle, we're going to plug in pi over 4. And then for the bottom part of r, we're going to plug in 0. And for the upper region of r, we're going to plug in the function cosine 2 theta. Now remember that wherever we put the dr in the polar coordinate integral, we have to introduce the scaling of r. So when we integrate the first part of the integral, which is with respect to r, the integral of r is going to be 1/2 r squared. And those bounds of integration are going to go from cosine 2 theta to 0. So that's going to leave us with 1/2 cosine squared 2 theta. And then we want to integrate this equation with respect to theta. Using the double angle formula, we can get a simpler representation for the cosine function. And then we just follow through with the definite integral as from calculus 2, and we end up with the result of pi over 8.